Imagine you're trying to train a small language model to become a capable agent, one that can call Python to solve math problems or issue search queries to answer questions. The natural approach is to have a stronger teacher model demonstrate how it's done, and then have the student imitate. But here's where things get tricky. If you just show the student the teacher's perfect trajectories and train it to copy them, the student learns to mimic behavior on prefixes it would never actually encounter because it makes different mistakes than the teacher. Then at inference time, when the student inevitably drifts off the teacher's path, it has no idea how to recover. Errors compound. The fix that's become popular is called on-policy distillation. The student rolls out its own trajectories, hits the environment, and at every step, the teacher whispers over its shoulder what it would have done. This gives you the best of both worlds. Dense, token-level supervision from the teacher, but on histories the student actually visits. The problem is cost. Every training update requires fresh rollouts through the environment, live Python interpreters spinning up, search engines being queried, and the teacher being called at every visited state. When you scale this to multiple environments or long horizons, it becomes brutally expensive. This paper asks a deceptively simple question. What if we just reuse the trajectories the teacher already generated? For instance, the rollouts collected while training the teacher itself with reinforcement learning, and never touch the environment during student training at all? You'd replay the teacher's prefix up to some step, let the student generate its action there, and have the teacher score that action. No live environment, no fresh tool calls, and if the teacher was trained with reinforcement learning, its rollouts are already sitting on disk as a free byproduct. But there's a subtle trap here, and this is really the heart of the paper. The authors call it the prefix trap. When you make prefixes fully student on policy, they're relevant to what the student will actually see at inference. But the teacher may be unreliable when queried on those weird student-induced histories because they're far from where the teacher itself would ever go. Conversely, when you use teacher-forced prefixes, the teacher's advice is trustworthy, but the histories don't match what the student would encounter on its own. This is a two-sided distribution shift, and it's fundamentally different from the usual on-policy story. Think of it like getting driving directions from an expert who's only ever driven on highways. If you take them onto back roads, their advice becomes unreliable. Not because they're a bad driver, but because you've queried them outside their zone of competence. The authors formalize this with a clean decomposition. The gap between your practical training objective and the ideal one you'd want is bounded by two terms. One measuring how much your effective prefix distribution differs from the student's true occupancy, and another measuring how unreliable the teacher's supervision is on those prefixes. Neither extreme minimizes both terms. So the right approach isn't just make it on policy, it's design a prefix distribution that balances student relevance against teacher reliability. They derive that the optimal effective distribution is a geometric bridge between the two occupancies, controlled by a mixing exponent that can vary per step. Now here's the clever practical move. Computing that exact bridge weight would require estimating a product of student-to-teacher likelihood ratios along the entire prefix. High variance and expensive, but when they plot that ratio against step index empirically, they find something beautiful. It decays smoothly and predictably with depth. Each factor in the product compares the student's probability of the teacher's own recorded action to the teacher's probability. And since the teacher chose that action, the ratio is typically less than 1. So the product shrinks geometrically as prefixes lengthen. This means step index alone is a strong proxy for the full reliability weight. So instead of computing complicated per-history ratios, they replace it with a single one-parameter schedule, a decay base key raised to the step index. Early steps get more training mass, late steps get less. That's it. The steepness of the decay is calibrated to the teacher-student capability gap. Wider gap, steeper decay. The algorithm itself is straightforward. Take pooled teacher trajectories. Sample supervised positions with probability proportional to C to the step. At each sampled position, replay the teacher's prefix verbatim, have the student generate its own action, and compute a per-token KL divergence between the student's distribution and the teacher's recorded conditional along that action. No environment calls, ever. The student's action is genuinely on policy at the supervised step, even though the prefix leading up to it isn't. The experimental results confirm two clean regimes. On mathematical reasoning with a Python tool, where the teacher-student capability gap is wide, ReOPD outperforms standard on-policy distillation across teacher scales. Under a QN38B teacher distilling into a 4B student, AME24 accuracy jumps from 28.3 to 36.7. On search tasks, where the teacher stays reliable on student-induced histories because the gap is small, ReOPD essentially ties on policy distillation at around 40.5% average. Meanwhile, ReOPD runs at least 4 times faster per rollout, uses 0 tool calls during student training, and requires no GPU-hosted retrievers or Python process pools. A particularly striking ablation shows that if you replace the teacher's own prefixes with prefixes from a stronger model, performance gets worse, vividly demonstrating that what matters is reliability of the teacher on those prefixes, not raw prefix quality. Now, for the caveats. The step decay schedule is a coarse proxy for the true reliability signal. It captures depth, but not the finer-grained question of how far a specific prefix wanders from teacher-supported territory. The authors use a fixed key of 0.6 across tasks, which works well, but a truly gap-adaptive or learned reliability estimator could do better. The approach also fundamentally depends on having a pre-collected teacher pool of reasonable coverage. If your teacher trajectories don't span the space of prompts you care about, the student can't learn beyond that support, and while replaying prefixes eliminates environment calls, you still need the teacher's per-step conditionals, which either means storing full logit distributions or querying the teacher offline once. Now let's walk through some questions you might have after hearing all of this. First, why exactly does teacher reliability degrade on student-generated prefixes? The teacher was trained on a certain distribution of histories, those induced by its own action choices interacting with the environment. When the student, being weaker, takes different actions, the environment evolves differently and produces states the teacher rarely encountered during its own training. The teacher's next token distribution on those states isn't wrong exactly, but it's less calibrated, more like extrapolation than interpolation. So its supervision signal becomes noisier and less trustworthy precisely where the student needs guidance most. Second, if the prefix is teacher-forced, in what sense is this still on policy? The distinction is subtle but crucial. On policy in this framing means the tokens being supervised are sampled from the current student. When the student generates its action at the supervised step, each token in that action conditions on the previous tokens the student itself just produced. So the loss is computed on the student's own distribution, matching what happens at inference. The prefix that came before is teacher-forced, but the specific step being trained is genuinely student-sampled. It's a hybrid, enough on-policy signal to fix the exposure bias problem, but with a teacher-anchored prefix to keep teacher supervision reliable. Third, why does a simple step decay schedule work so well when the theory suggests you'd want a more nuanced per-history reliability estimate? The author's empirical plot in Figure 4 is really the answer here. When they actually measure the exact reliability ratio prefix by prefix, it clusters tightly by step index. Depth explains most of the variation because each step of teacher prefix compounds another factor of the student-teacher divergence. So, a schedule based purely on position captures the dominant signal, and adding more complexity would mostly add variance without capturing much additional structure. It's a case where a coarse proxy happens to align well with the underlying quantity you'd ideally measure. Finally, thinking about how these ideas transfer to large-scale recommendation systems. In production ranking and retrieval, you often have a strong teacher model, say a heavy transformer scoring model or an LLM-based reasoning system for query understanding. And you need to distill it into something cheap enough to serve at millions of queries per second. The on-policy distillation problem shows up because the student, once deployed, encounters a session distribution shaped by its own ranking decisions, not the teacher's. But rerunning the teacher over live student sessions during training is prohibitively expensive when your teacher involves LLM calls or heavy cross-encoders. ReOPD's core insight, that you can replay teacher-recorded interaction traces with a reliability-aware weighting that emphasizes early, low-shift positions, directly applies. You'd cache the teacher's session-level rollouts from historical logs, Train the student to imitate the teacher's per item scores conditioned on those replayed session prefixes, and weight the loss to concentrate on the early session turns where the teacher and students' induced session dynamics haven't yet diverged. The multi-environment result is especially relevant for large platforms with heterogeneous surfaces: feed ranking, search ranking, notification ranking, ads. Each surface has its own environment and its own domain expert teacher. Rather than keeping all these environments live during joint training of a shared foundation ranker, you could collect each teacher's rollouts once, merge them into a unified offline pool, and train the shared student purely off environment. That's a substantial operational simplification when you're trying to consolidate ranking stacks across dozens of surfaces without maintaining live coupling to every downstream environment during every training run.